boy, we're nearly at 1,000 subscribers. It's too bad Super Smash Bros. Ultimate's coming out soon. Once Smash hits, I'll be done with this math teacher gig and training to become a professional smasher. Like the Hulk, but with more dexterous thumbs. But what's the probability that I actually make it as a professional Smash player? Well, the probability of an event has to be between 0 and 1, so it's probably somewhere in there. Oh, there it is. No, wait a minute, what's this? 0.00000003. The probability of 4 randomly selected Smash Bros. Ultimate characters, all being Luigi. There's a great point to take away from the fact that I used Luigi in that probability. As a teacher, we need to be aware of how people might take the things we say, and if that probability had referred to 4 Marios, then people might have been confused, wondering does that include Dr. Mario too, or just normal Mario? With Luigi, there's no room for confusion, because the only other Luigi-y character is an assist trophy. Super Smash Bros. Ultimate. It's the newest installment in Nintendo's crossover fighting series, and it comes out very soon. There's a total of 32 different video game franchises represented in this game, not counting one little bugger from my favorite franchise, probability. Oh yeah, we're talking about that seductive random button. Choose random on the character select screen, and you'll end up with a random character from the massive cast of 74. If you and 3 friends all choose random, you're probably not going to all end up with Luigi. But what are the odds that you all end up with 4 characters in the same franchise? That's the question we'll be exploring today. And we've got a really fun giveaway at the end, but all of this math stuff is going to be pretty important to that giveaway. Hey everyone, and welcome to episode 1 of my new series, Math Lab. Math Lab is all about answering and exploring fun and interesting problems that let us use and hone our math skills without assuming that you already know all of the math that we're going to use. With all the math you already know, some critical thinking, and a few Google searches, you can solve some pretty cool problems. A math lab is just like a science lab, except way better, because horsing around is completely permitted. Oh man, with so much math to do, I don't even know where to start. Let's go back to the question and make sure we know exactly what we're asking. If 4 players all randomly select their character in Super Smash Bros. Ultimate, what is the probability of all 4 characters being from the same franchise? We'll call a match where all characters are from the same franchise an all-franchise match, and a match where not all characters are from the same franchise a cross-franchise match. So that's simple enough. But to make our question clear, we need to define the terms in the question. Let's start with random. That's pretty easy, right? Randomly selecting your character just means you picked random on the character select screen. Done and done. Obviously the random button's random, right? The game generates some sort of list, giving each character a higher odd of being played after X sets. Never rolls dittos. Characters with alt skins have 20 to 25% chance of occurrence. As a random main, biased towards default costumes. You will cycle through all of them before the deck is reshuffled. The random is biased, so you go through more characters. As a random main, stopped reading right there. Same. The order is determined based on the seed value at CSS start, repeatedly randomly selecting characters gave me the sequence Pichu, Ganondorf, Luigi, resetting the save state and doing the same thing always gave me that sequence. Jeez, Lou! Okay, so the random button isn't truly random in the past Smash Bros. Games, and it probably isn't going to be in the new Smash either. I don't want to spend 10 minutes talking about how the random button works, so we're going to assume it works how we want it to. But if you want some more details on the random button, go to the description where I talk about the giveaway. The random button is involved in that discussion. We are going to assume that all characters are equally likely to be randomly selected by one player, and that no character can be randomly selected by more than one player. If one player has already randomly selected Luigi, no other player can randomly select Luigi, which means there are no repeats allowed. So for all randomly selected characters to be in the Super Mario franchise, we need something like Luigi, Bowser, Daisy, and Peach. Luigi, 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 Luigi is not going to cut it. This seems to be pretty close to how the random button works in Smash Bros. Finally, what does it mean for characters to be in the same franchise? How do we determine if Luigi belongs to the Super Mario franchise or the Luigi's Mansion franchise? Who has the right to say? Thankfully, this question's easy. We'll use the franchise listings on the official Super Smash Bros. Ultimate website. Using this source tells us that indeed, Luigi does belong to the Super Mario franchise, but Wario does not.
So I missed!
Additionally, using this list to give us the official character count, we get a total of 75 characters, but we aren't going to count Piranha Plant because he isn't coming out until next year, so there are 74 characters and 32 franchises. Alright, all the boring preliminary stuff is out of the way, which means it's time to get down to business. To get your mind in the right space, let's answer an easy character selection question. If we randomly select a Smash Ultimate character, what's the probability of selecting Luigi? We can write that like this: P for probability of an event, and then in the parentheses we put the event we are talking about. Alright, there's one Luigi, there are 74 total characters, all equally likely to be selected. What's the probability of selecting Luigi? It's 1 divided by 74. The total number of ways of selecting Luigi, 1, divided by the total number of ways of selecting a character, 74. That is a probability of approximately 0.014, or 1.4% for those of you who like percentages. This is exactly how we're going to calculate the probability of getting 4 characters in the same franchise. It's a classic probability law, passed down from wise man to wise man, and finally to us. If we are running an experiment with n possible outcomes that are all equally likely, then the probability of an event E occurring is the number of ways E can occur divided by n. Let's look at one more example. What's the probability of randomly selecting a character from the Super Mario franchise? Again, there are 74 possible outcomes, all equally likely. There are 8 ways to select a Super Mario character: Mario, Luigi, Peach, Daisy, Bowser, Dr. Mario, Rosalina, and Bowser Jr. So, the probability is 8 divided by 74, or approximately 0.108 or 10.8%. Alright, with the wisdom of ages now in our hands, we can answer the question we desire. What is the probability of randomly selecting 4 distinct characters that are all from the same franchise? What do we need to do first? We need to find n, the number of possible outcomes our experiment has. The experiment is having 4 players randomly select a Smash Ultimate character, so how many outcomes are possible? To figure that out, we need to understand combinations. A combination is an unordered selection of k items from a collection of n items without repetition. So for example, Mario, Pikachu, Olimar, and Samus is one possible combination of 4 Smash Ultimate characters. The order doesn't matter, and repetitions aren't allowed. We need to know how many combinations of 4 Smash Ultimate characters are possible. That's going to be a decently large number. Let's warm up with a small example to drive home what combinations are. Let's say you're considering 3 games for the Nintendo Switch, but you're only going to buy 2 of them. Let's say you're considering Mario Odyssey, Mario Kart 8, and Zelda Breath of the Wild. This is a collection of 3 items, so how many combinations of 2 games are there from this collection of 3 games? You could get Mario Kart and Zelda, or you could get Zelda and Mario Odyssey, or you could get Mario Kart and Mario Odyssey. So there are 3 possible combinations of 2 items from a collection of 3. With our Smash Ultimate experiment, we are selecting 4 characters from a total of 74. How many combinations are there? Well, thankfully for us, there's a formula for combinations, so let's use that. The formula for this is actually the formula for what are called binomial coefficients, which you should totally look up if you're remotely interested. It's really cool how these different topics in math cross over. Alright, so the formula. The number of possible combinations of 4 characters from a collection of 74 characters, often written like this, is equal to 74 factorial divided by 4 factorial times 74 minus 4 factorial. Also, as a side note, you can read this notation here as 74 choose 4. If you say that to Siri, she will know exactly what you were talking about. Okay, factorials. In case you're not familiar with them, they work like this. 4 factorial is equal to 4 times 3 times 2 times 1. 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. 74 factorial is equal to 74 times 73 times 72 times 71 times 70. You get the picture. To briefly explain why this formula works, the 74 factorial up here is the total number of ways we could order the 74 characters in Smash Ultimate. Dividing by 74 minus 4 factorial brings that number down to the total number of ways to order 4 characters from the collection of 74. Finally, dividing by 4 factorial gets rid of the extra orderings, meaning all we are left with is the number of ways to select 4 characters from a collection of 74 where order doesn't matter. To finally get this number, let's ask Siri. 74 choose 4.
The answer is 1,150,626.
Ooh boy, that's a thick number right there. 1,150,626 possible combinations of 4 Smash Ultimate characters. Now we know the number of possible outcomes of our experiment, so to find the probability we're looking for, we just need to find the number of ways we can select 4 distinct characters all from the same franchise, then divide that by the total number of possible outcomes. Thankfully, with a little bit of thinking and our combination formula, we'll be able to get there in no time. Counting the number of ways we can select 4 characters from the same franchise is a little more complicated than the previous step, but not by much. We just have to look at each franchise individually, figure out how many ways we can select 4 characters from that franchise, do that for all 32 franchises, and add those numbers up. Let's start off looking at the Donkey Kong franchise.
Yeah, Donkey Kong, yay!
How many ways can we select 4 characters from this franchise? Are you seeing what I'm seeing? It's 0. There are no ways to select 4 characters from the Donkey Kong franchise because it only has 3 characters in the game. Since we aren't allowing repeats, there are no ways to select 4 characters from this franchise, so it contributes 0 to our running total. Yoshi, same thing. Kirby, same thing. Star Fox, Earthbound, F-Zero, Ice Climber, Game & Watch, Kid Icarus, WarioWare, Sonic the Hedgehog, Pikmin, Rob, Animal Crossing, Mega Man, Wii Fit, Punch-Out, Me, Pac-Man, Xenoblade Chronicles, Street Fighter, Final Fantasy VII, Bayonetta 2, Splatoon, and Castlevania. Throw them all in the trash. They all contribute 0 to our running total. Our running total isn't running very quickly. So what franchises are left? Only Mario, Zelda, Metroid, Pokemon, and the anime Sword Boys. We'll start with Metroid since that's the easiest. It's got 4 characters. How many ways can we select 4 characters from the Metroid franchise? Just one way. Samus, Dark Samus, Zero Suit Samus, and Ridley is the only possible all-Metroid matchup. So finally, our running total of possible all-franchise matchups gets to 1. Next, let's look at the Super Mario franchise. It has 8 representatives, again we're not counting Piranha Plant. So how many combinations of 4 characters from the Super Mario franchise are possible? Easy. It's just the combination formula we used earlier, but now with a collection size of 8, because we are choosing 4 characters only from the Super Mario franchise. That's 8 choose 4. Let's consult Siri to get this calculation quickly. 8 choose 4.
The answer is 70.
Alright, there are 70 possible combinations of 4 Super Mario characters, so our running total is now 71. Moving on to The Legend of Zelda, this franchise has 6 representatives. The number of combinations of 4 characters from this collection of 6 is equal to 6 choose 4. That's equal to 15. Our running total is now at 86. It's growing, but not really relative to that 1.1 million. Now on to the Pokemon franchise. It has 8 representatives, just like the Mario franchise. We already did that calculation, 8 choose 4, that's 70. Add that to our running total, we're at 156. Finally, the last franchise to be considered, the Fire Emblem franchise. It has 7 representatives, so the number of combinations of 4 characters from the Fire Emblem franchise is 7 choose 4. That's 35, putting our final total at 191. Of the 1,150,626 possible combinations of 4 Smash characters, only a minuscule 191 of those combinations are all franchise matchups, so this is going to be a pretty tiny probability. To get the probability we seek, we take 191 divided by 1,150,626, and that gives us approximately 0.000166. That's pretty unlikely, but it's over 50,000 times as likely as winning the Mega Millions jackpot, according to odds given by CNBC in October of this year. Comparisons to the lottery are all well and good, but I'm not really sure they help illuminate this probability that much. The numbers are too small. If you and your friends want to just play random smash matches over and over again until you get an all-franchise match, does this number really tell you that much? By itself, no, but we can use it to answer a much more interesting question that will help illuminate just how likely or unlikely this event really is. So we found the probability that 4 randomly selected Smash Ultimate characters are all from the same franchise, but before we go, we're going to get down and dirty to answer one more question. How many times would we have to randomly select 4 Smash Ultimate characters so that it is more likely than not that we get at least one all-franchise match? We'll also calculate how many times we'd have to randomly select 4 Smash Ultimate characters for it to be more than 99% likely that we get at least one all-franchise match. This might seem like a fairly complicated problem, but with the wrath of math at our disposal, with the power of probability theory, this problem is a low-tier chump. As a matter of notation and convenience, we're going to have to introduce what is called a random variable to solve this problem. Random variables are supremely awesome and incredibly important, so don't snooze on this part. Basically, a random variable is a variable that takes on certain values depending on the outcome of a random phenomenon. Let's introduce the random variable we are going to use in order to clarify this concept. We're going to let the random variable x be the number of occurrences of an all-franchise match in k trials. The reason we're using k trials instead of some non-variable number is that k is the number we're trying to figure out. We don't know what it is. You'll see what I mean in a minute. But to finish this little micro lesson, let's just say that k is 100. So we randomly select 4 Smash Ultimate characters 100 times. Then our random variable x is the number of all-franchise matches we get in those 100 trials. If we got 2 all-franchise matches, then x is 2. If we got no all-franchise matches, then x is 0. You can see how the value of x varies depending on the outcome of this random experiment. Also, notice that x has to be a non-negative integer, 0, 1, 2, 3, and so on, because we can't have half of an all-franchise match in k trials, and we can't have a negative number of all-franchise matches in k trials. Now, clear your mind of that k value we were working with. We don't know what k is. The question, again, is how many times would we have to randomly select 4 Smash Ultimate characters for it to be more likely than not that we get at least one all-franchise match? Translating this question into language with our new variables gives us this. What must k be equal to so that the probability of x being greater than or equal to 1 is greater than 1/2? This is actually a bad question, because it has infinitely many answers. The question we should be asking is this: what is the smallest value of k, so that the probability of x being greater than or equal to 1 is greater than 1/2? We know we could run our trial 1 trillion, or 2 trillion, or 7 nonillion times, and we'll probably get at least one all-franchise match in there, but we want to know the smallest number of trials, so that it's more likely than not that we have at least one all-franchise match. There's only one answer to that question. To break the question down, the smallest value of k is the minimum number of trials we're trying to calculate. X being greater than or equal to 1 means there is at least one all-franchise match in those k trials, and we want the probability of this occurring to be greater than 0.5, because that means it is more likely than not that it occurs. Now another fighter joins the battle, the law of complement. I'm loving all the good stuff we're getting in this lab. The law of complement is another classic probability result that's extremely simple, but also unbelievably useful. The law of complement tells us that the probability of an event happening plus the probability of the event not happening is equal to 1. It's basically the formal version of it does or it don't. I've actually never heard anyone say that, but I think you get my point. An event either happens or it doesn't happen, so if you add up their probabilities, you get 1. It's guaranteed that it will either happen or it will not happen. So why is this useful for us? Well, we know that x can take on values of 0, 1, 2, 3, all the way up to k. These are the possible numbers of all franchise matches in k trials. Then, with the law of complement in our back pocket, we know this is true. the probability that x is 0 plus the probability that x is greater than or equal to 1 is equal to 1. Do you see why this works? X has to be either 0 or greater than 0, so the probabilities of these two possibilities must add up to 1. Now, we can move either of these probabilities over to the other side of the equation by subtracting, and we're going to use the other one to solve for k. So which probability should we subtract, and which should we use to solve? Well, the probability that x equals 0 is just that. Simple. It's one number, the probability that x equals 0. The probability that x is greater than or equal to 1, on the other hand, is the probability that x is 1, plus the probability that x equals 2, plus the probability that x equals 3, and so on, all the way up to the probability that x equals k. Which one of these would you rather work with? Yeah, let's use the 0 one. Then we'll subtract the probability that x is greater than or equal to 1 from both sides, giving us 1 minus the probability that x is greater than or equal to 1 equals the probability that x equals 0. Remember that the whole point here is to find the smallest k that makes it more likely than not that x is greater than or equal to 1. That's the smallest amount of random matches we would have to play so that it is more likely than not that we get at least one all-franchise match. So, for our purposes, the probability that x is greater than or equal to 1 is greater than 1/2. So then 1 minus the probability that x is greater than or equal to 1 is less than 1 minus 1/2. This is true because in this quantity we are subtracting more from 1 than we are over here, because the probability that x is greater than or equal to 1 is greater than 1/2. Finally, since this is equal to this, and this is less than this, we have that the probability that x equals 0 is less than 1/2. We want to find the smallest value of k that makes this inequality true. I can smell it now, we're so close. You might notice that there's no k in this expression, so how are we supposed to solve for k? We're going to have to replace this with something else. Thankfully, that's a breeze. If we run k trials of our experiment, and after all k of them x equals 0, that means that every single randomly selected match was not an all-franchise match. So the probability that x equals 0 is the same as the probability that all k trials were cross-franchise matches. But what is the probability of a cross-franchise match occurring? To figure this out, we just use the law of complement again. A match has to be either an all-franchise match or a cross-franchise match. So the probability of an all-franchise match plus the probability of a cross-franchise match is equal to 1. We already calculated this probability. It's about 0.000166, so subtracting it from both sides gives us exactly what we're looking for. The probability of a cross-franchise Smash Ultimate match is approximately 0.999834. Unsurprisingly, it's very likely that if you randomly select 4 Smash characters, you'll be getting a cross-franchise match. So what if we have k random matches? What is the probability that they are all cross-franchise matches? Now I know what you're thinking. You're thinking, gee, we haven't gone over enough super important probability rules yet. We need more probability rules. Well, you're in luck. We're about to whip out another MVP candidate. The product rule. The product rule tells us that the probability of 2 or more independent events all occurring together is just equal to the product of their probabilities. What are independent events, you might ask? Basically, events are independent if they have no effect on each other. For example, coin flips are independent events. What happens when I flip this coin has no impact on what happens when I flip this coin. The probability that this coin lands heads up is 1/2. The probability that this coin lands heads up is also 1/2. The probability that both coins land heads up is 1/2 times 1/2, which is 1/4. Ah, they both landed heads up. If events are not independent, we call them dependent. I was tempted to give you an example of dependent events, but as the script for this video gets longer and longer, the probability that I choose to elaborate on more concepts gets smaller and smaller. So how about our little Smash Ultimate character selection experiment? If we run k trials of randomly selecting 4 random characters, does the outcome of any of those trials have an effect on the outcome of any other trial? We will assume the answer is no. They don't have any effect on each other. All trials are independent. However, in the actual game, this situation might be a little more complicated. In the game, you should be able to run independent trials. It's just a little tricky. Again, if you want to know more about that, just head to the description. But for now, we'll just assume the trials are independent. Okay, with all that humdrum explanation out of the way, since our trials are independent, we can use the product rule to rewrite this probability. By the product rule, the probability that all k trials result in cross-franchise matches is 0.999834 times 0.999834 times 0.999834 over and over again until you've got k 0.999834s getting multiplied together. Using exponents, we can rewrite this as 0.999834 to the power of k. So then we have 0.999834 to the power of k is less than 1/2. Huzzah, we're almost there. Now we need to notice something very important. What happens to this value, 0.99834 to the power of k, as k gets larger? What happens is 0.99834 to the power of k gets smaller. The more times we multiply by a positive number less than 1, the smaller our product. So as k increases, this whole value decreases. Here's a graph of y equals 0.99834 to the power of x, just so you can see this in action. As x gets larger, y gets smaller. This is Desmos, by the way. It's free and is just wonderful. Definitely check it out if you're interested. So why do we care that this is decreasing? Well, remember, we're trying to find the smallest value k so that 0.999834 to the power of k is less than 1/2. So here's 0.999834 to the power of k. Here's 1/2. This value is getting smaller and smaller until eventually, bam, for some value, let's call it x, 0.999834 to the power of x is equal to 1/2. Then, for any value of k that is greater than x, 0.999834 to the power of k is going to be less than 1/2, because the greater the exponent gets, the smaller the value of the expression gets. We're trying to find the smallest k value so that 0.999834 to the power of k is less than 1/2. So we're trying to find the smallest k value that's greater than x. Remember that k is the number of trials, so it has to be a non-negative integer. So we need to find x and then find the smallest integer that is greater than x. I think this is the most complicated part of the episode, but it's important, so feel free to rewind a little bit and watch that explanation again if it wasn't clear. Now, to find x, remember that x satisfies this equation. 0.999834 to the power of x equals 1/2. We want to get x by itself, but it's currently trapped in this exponentiation. Do you know how to solve this equation? If not, then you probably either forgot or have yet to learn about logarithms. Here's how logarithms work. If we are multiplying tens, how many do we need to get 1,000? 3, right? 10 times 10 times 10 is 1,000, so 10 to the power of 3 is 1,000. We need to raise 10 to the power of 3 to get 1,000. Thus, the logarithm of 1,000 with base 10 is equal to 3. The logarithm of a number a with a base b tells us the number c, so that b to the power of c is equal to a. It answers the question, what power must we raise b to in order to get a? The logarithm of 9 with base 3 is equal to 2, because we must raise 3 to the power of 2 in order to get 9. The logarithm of 16 with base 2 is equal to 4, because we must raise 2 to the power of 4 in order to get 16. The logarithm of 7 to the power of 9 with base 7 is equal to 9, because we must raise 7 to the power of 9 in order to get 7 to the power of 9. An easy way to remember how this works is log base answer equals exponent. This base to the power of this exponent gives this answer. So we need to take the logarithm of both sides of this equation to get x by itself. What should the base of our logarithm be? Well, this is the exponent we're trying to solve for, so the base of our logarithm should be the base of this expression, 0.999834. Taking this logarithm on both sides, we have the logarithm of 0.999834 to the power of x with base 0.999834 is equal to the logarithm of 1/2 with base 0.999834. This side simplifies nicely. What power do we have to raise 0.999834 to in order to get 0.999834 to the power of x? If you don't immediately know the answer, repeat the question. What power does this need to be raised to get itself to the power of x? It needs to be raised to the power of x, of course. So on this side, we just have x as desired. On this side, we have the logarithm of 0.5 with base 0.999834. We can plug that into a logarithm calculator, which gives us about 4,175.2. Then, the smallest integer greater than this is 4,176. This is it. This is the smallest number of times we would have to randomly select 4 Smash Ultimate characters so that it is more likely than not that we get at least one all-franchise match. We would have to randomly select 4 Smash Ultimate characters 4,176 times, and even then, it's just barely more likely than not that we get an all-franchise match in those 4,176 attempts. But let's up the ante. Let's say we want supreme confidence. What's the smallest number of trials we'd have to run so that it's more than 99% likely that we get at least one all-franchise match? If we truly want to get one of these one-franchise matches in a game that's all about franchises crossing over, how many matches do we need to be ready to play? Thankfully, this is an easy question now. We already did all the hard work. Before, it all boiled down to taking the log of 1 minus 1/2 with base 0.999834. Now, we just take the log of 1 minus 0.99, again with base 0.999834. This is the logarithm of 0.01 with base 0.999834. Going to our calculator again, we see this is approximately 27,739.7. Again, we go to the smallest integer that is greater than this number, and that is 27,740. We would have to run our trial of randomly selecting 4 Smash Ultimate characters nearly 28,000 times in order for it to be more than 99% likely that we get at least one all-franchise match. What if each time we randomly selected 4 characters, we actually played the match? Suppose each match takes 3 minutes. That's nearly 60 days of playtime. You have to be ready to play 2 months straight of just randomly selecting characters and playing each match in order to be 99% sure that you'll get an all-franchise match somewhere along the way. Wow. Who would have thought something so simple, randomly selecting 4 characters from the same franchise, would be so difficult to achieve? Well, if you're up for the challenge, I'd like to see one of these random all-franchise matches actually occur, so I'm doing a giveaway. The first person to send me a video of them randomly selecting 4 characters, all from the same franchise, in Smash Ultimate will win their choice of a Smash Ultimate GameCube controller with an adapter so that you can actually use it, or the wireless PowerA GameCube controller, which needs AA batteries, or the hardcover Super Smash Bros. Ultimate Official Collector's Edition Guide. It's your choice, you just have to send me that video. All the details are in the description. You can also find them on all my social media. Links to all of that down in the description. Please read those details so you know exactly what I'm looking for so that you don't waste it if you do get one of these rare matches. Also, please don't waste too much time on this. Getting one of these matches randomly is really unlikely. You could spend your time learning more math, enjoying the game, or earning money to go and buy all of the stuff that's in the giveaway. This is just some incentive for you to give it a few goes. I'm interested to see if somebody can actually get one of these matches. If you're interested in seeing that too, share this video around so that more people can learn some math and more people can try to win the giveaway. I hope you all enjoyed the first episode of Math Lab. If you have any questions about any of the math that we did in the video, or any related questions that you're curious about, don't hesitate to ask down in the comments. If you want to see more Math Labs, let me know in the comments, and if you want to share any ideas for new episodes, episodes, please do. Thank you very much for watching. I'll see you next time, and be sure to subscribe for the swankiest math videos on the internet.
What's stopping me? Lobotomy. I lift the weight that's drowning me so I can rise up to the sea. I wasted half my breath on her, she's not wasting her breath on me. Rise like a phoenix from the ash, my lungs filled to capacity with smoke from my past stacking up.